In a quiet lab, a machine the size of a chandelier just solved a problem in 5 minutes that would take the fastest supercomputer 10 septillion years. And the answer it gave back terrifies physicists. Because to get that answer, the machine seems to be reaching into places that should not exist. Parallel worlds, hidden dimensions, a reality beneath reality. If you want to know what these strange machines have uncovered, hit subscribe and stay close. We're about to explore particles that exist in two places at once, computers that whisper to other universes, and a discovery that suggests everything you see may be a projection. Brace yourself. We begin. Picture a refrigerator made of gold, hanging upside down from the ceiling of a windowless room. Wires spiral down its sides like the roots of a metal tree. Inside, the temperature drops colder than deep space, colder than the surface of any planet, colder than anything in the known universe outside of laboratories like this one. This is a quantum computer. It does not look like the laptop on your desk. It does not hum like a server rack. It whispers, almost silently, as helium liquid cools its core to a fraction of a degree above absolute zero. And inside that frozen heart, something impossible is happening. A regular computer thinks in coins, heads or tails, 1 or 0, every photo on your phone, every song you stream, every word in this script, all of it is built from trillions of tiny switches flipping between two answers. Yes or no, on or off, nothing in between. A quantum computer does not play that game. It uses something called a qubit, and a qubit refuses to choose. Flip a normal coin and it lands. Flip a quantum coin and it stays spinning forever in the air. Heads and tails at the same time. Both answers, neither answer, all answers blurred together until something forces it to land. Now stack 2 of those spinning coins, then 4, then 100. Each one holds every possibility at once. The math explodes. 60 qubits working together can hold more possible states than there are grains of sand on Earth. 300 qubits can hold more states than there are atoms in the visible universe. 300 tiny switches holding more possibilities than every atom that exists. How is that even physically possible? That question is exactly what scares physicists. Because nobody, not one person on Earth, can fully explain where all that information lives. The chip is small. The room is finite. But the calculations behave as if the machine is borrowing storage space from somewhere else. Somewhere we cannot see. Somewhere that may not even be in our universe. One famous physicist, David Deutsch, says the only honest answer is that quantum computers are tapping into other realities. Parallel versions of our world, running side by side with ours, doing the same math. When the machine returns an answer, those parallel calculations collapse into ours. Most scientists call that idea wild. Some call it the only explanation that fits the data. None of them can rule it out. Major laboratories in California, Beijing, Munich, and Sydney are now racing to build bigger machines. Google has one, IBM has one, China has several. Each new generation does things the previous one could not, and each new generation deepens the mystery instead of solving it. We are building tools that work. We just have no idea why they work. In the next chapter, we look at a specific machine called Willow, built by Google, and the moment it performed a calculation so impossibly fast that the team running it had to sit down, because the only number that matched their result was a number bigger than the age of the universe itself. December 2024. A team of engineers in Santa Barbara stood around a screen in silence. Their machine had just finished a test problem. The clock said 5 minutes had passed. The math told a very different story. To do the same problem on the world's fastest classical supercomputer, a machine called Frontier, the size of 2 basketball courts, would take 10 septillion years. Let that number breathe for a moment. 10 septillion. That is a 1 followed by 25 zeros. The universe itself is only about 14 billion years old. The number of years Frontier would need is so much larger than the age of the universe that it makes the universe's lifetime look like a single heartbeat. Their machine had done it during a coffee break. The chip is called Willow. It is roughly the size of a postage stamp. It holds 105 qubits, the special quantum switches we met in the last chapter. And what Willow demonstrated that day was something the field had been chasing for over 2 decades. Something called quantum supremacy with error correction. To understand why this is terrifying, you have to understand the old problem. Earlier quantum computers were fragile. The smallest disturbance, a single stray particle, a tremor, a whisper of heat, would scramble their answers. Add more qubits, and the noise grew faster than the power. It was like trying to read a book during an earthquake while someone shook the lamp. Willow flipped that curse. The Google team showed that as they added more qubits, the errors got smaller, not bigger. The machine started healing itself. That sounds technical. The implications are not. It means quantum computers are no longer a fragile science experiment. They are crossing into the territory of practical, reliable, world-changing tools. And it means the timeline for everything else, code breaking, drug design, simulating the laws of physics, just collapsed. But the strangest part is not what Willow did. It is how it did it. The benchmark problem it solved is called random circuit sampling. Imagine shuffling a deck of cards in a very specific way and asking how often each possible arrangement comes up. With normal decks, the answer is huge, but finite. With Willow's quantum deck, the number of possible arrangements is larger than the number of particles in the observable universe. Frontier would need to track every one of those possibilities, one at a time. Willow seems to consider them all at once. How does one chip do the work of a calculation that should require more computing power than exists on Earth? Where does that processing actually happen? The Google team did not answer that question in their press release. They simply published the result and let the physics community argue. And argue they did. Within days, papers appeared with titles asking whether Willow had provided new evidence for the existence of parallel universes. Hartmut Neven, the head of Google's quantum lab, was asked the question directly. His answer was careful. He said the calculation lends credence to the idea that we live in a multiverse, that the universe is not alone. The boss of the team that built the machine had to admit, out loud, that he was not sure whether his computer had been borrowing power from other worlds. Next, we look at the qubit itself. Hold out your hand. Imagine balancing a coin on its edge in your palm. Heads on one side, tails on the other. You do not push it. You do not flip it. The coin simply stands there, perfectly still, refusing to fall either way. That is impossible in your kitchen. That is normal inside a quantum computer. A qubit is the basic ingredient. The word stands for quantum bit, and it is the strangest building block ever made by human hands. Some qubits are tiny loops of superconducting wire, smaller than a grain of rice. Others are single atoms held in place by lasers. Some are electrons trapped in synthetic diamond. The shape changes. The trick is the same. A regular bit, the kind in your phone, must be either 0 or 1. Always one of the two. Never both. A qubit refuses that rule. It can be 0. It can be 1. It can be both. Woven together in a single state called superposition. If that sounds like word salad, try this picture. Imagine standing at a crossroads where one path goes east and one goes west. A regular bit must pick a direction and walk. A qubit walks both paths at the same time, not by splitting in two, not by guessing. The qubit is, somehow, on both roads at once. Then comes the cruel twist. The moment you check on the qubit, the moment you measure it, the spell breaks. The coin lands. The crossroads collapses. You see only one answer, and the other vanishes as if it never existed. This is not a metaphor. It is the actual rulebook of the smallest scale of reality. Every experiment ever performed on quantum systems confirms it. Look away, and a qubit holds every possibility. Look at it, and reality picks one. Physicists have a name for this collapse. They call it the measurement problem. They have argued about it for 100 years. They still have no agreed answer about why looking should change anything. Think about what that means. The universe seems to behave differently depending on whether or not you are paying attention to it. A qubit on its own is strange enough. The real power comes when you connect them. Two qubits can be linked so tightly that touching one instantly affects the other. Add more, and the system holds a number of states that grows by a factor of 2 with every qubit you add. 10 qubits, 1,024 states. 20 qubits, more than 1,000,000. 50 qubits, more than 1,000 trillion. That growth is exponential, which is a word people often use loosely. Here it is exact, and it is terrifying. A modern chip with a few hundred qubit stores, in superposition, more possible configurations than there are atoms in your body. In your house, in your city, in the planet Mars, in the sun. The numbers stop being numbers and start being symbols of something we do not understand. And every one of those configurations is real in some sense until the moment someone reads the answer. In the next chapter, we step back from the machine and into the act of looking itself. Because the rules say that observation does not just record reality, it builds it. You are watching a film. The actors move, the story unfolds. Whether or not you are in the room, the film keeps playing. The world, you assume, works the same way. The moon is up there whether you look at it or not. The chair behind you exists when your back is turned. That assumption is older than civilization. And at the smallest scale of reality, it appears to be wrong. When physicists peer at single particles, the rules change. A particle, left alone, does not have a definite location. It does not have a definite speed. It does not even have a definite kind of behavior. It is smeared out into a cloud of probabilities, a ghostly mist of every place it might be, and every way it might act. Then, someone looks. The cloud snaps. The particle picks a spot. The mist condenses into a point, and the moment the human, or the instrument, or the camera turns away, the point dissolves back into mist. This is the measurement problem in plain language. Reality at the bottom seems to wait for an audience. Albert Einstein hated this idea. He once snapped at a friend, asking whether he really believed the moon was not there when nobody was looking. Einstein wanted a universe that existed solidly, on its own, with or without people. He spent the last 30 years of his life trying to prove that the quantum rulebook must be incomplete. Every experiment proved him wrong. You might think this only happens to invisibly small things. Atoms, electrons, photons, but the trick scales up. Researchers have run the test on molecules made of hundreds of atoms. The molecules behaved like fuzzy clouds when nobody watched. They behaved like solid points when somebody did. Larger and larger objects have been pulled into the strange game. There is no known size limit. The only reason your coffee cup does not vanish into a probability cloud is that countless particles around it are constantly bumping into it, watching it for you. In other words, the universe itself is the audience for everything bigger than a speck. The world feels solid because trillions of tiny eyes, air molecules, photons, vibrations, are always staring at it. Strip that audience away, and solidity goes too. A quantum computer is a machine that strips the audience away on purpose. The whole point of the cold, the shielding, the careful isolation, is to give the qubits a private room where nothing watches them. In that private room, they hold every possibility. The instant someone measures the result, the room is invaded, the audience returns, and the answers crystallize. This raises a question that should keep you awake. If reality at the bottom needs observation to settle, what was happening before there were any observers? Before life? Before stars? Before atoms? Did the universe exist as a soup of pure possibility, unfocused, undecided, until something looked? Some physicists, including the late John Wheeler, took that question seriously. Wheeler proposed that observers, including us, might be part of how the universe finishes itself, that we are not bystanders watching a finished show. We are participants helping the show happen. The next chapter shows the single experiment that started all of this, a piece of cardboard with 2 slits in it, and a result so impossible that physicists still cannot explain it. A piece of dark cardboard, 2 narrow slits cut into it, a wall behind it, a lamp in front of it. That is all you need. This is the most famous experiment in modern science. It is simple enough to set up in a high school. It is so disturbing that physicists have argued about it for over 200 years. Richard Feynman, one of the sharpest minds of the 20th century, said it contained the only real mystery of quantum mechanics. Here is what happens. Shine a light through the 2 slits. On the back wall, you see a striped pattern. Bright bands, dark bands, bright bands, dark bands. The light is behaving like a wave, with peaks and troughs that add up in some places and cancel out in others. Throw a stone into a pond near 2 openings in a fence, and the ripples on the other side will make the same pattern. That part is old physics. It made sense in 1790. It still makes sense today. Now fire single particles instead. 1 electron at a time, 1 photon at a time. Each one tiny, alone, separate, each one heading toward the cardboard. You would expect them to act like marbles. Some go through the left slit, some go through the right. They pile up in 2 clumps on the wall behind. Simple, solid, boring. That is not what happens. The striped pattern still appears. The single particles, each shot one by one, build up the same banded image as the wave, as if each electron passed through both slits at the same time and interfered with itself. Read that sentence again. 1 electron, 2 slits, both, simultaneously. So far this is strange but tolerable. Maybe the electron is some kind of wave. Maybe it spreads out, slips through both, and then lands as a dot when it hits the wall. Now comes the part that ruins your weekend. Put a tiny detector at one of the slits, just enough to peek and see which slit each electron went through. Run the test again. The striped pattern vanishes. The electrons start landing in 2 clumps, like marbles, like the simple version you expected. They go through 1 slit at a time, like polite particles. Turn the detector off. The stripes come back. The single particles return to passing through both slits at once. The act of watching, the simple act of measurement, changes the behavior of the particle, not how we describe it, how it actually behaves. This experiment has been repeated in thousands of labs around the world, with electrons, with photons, with whole atoms, with molecules made of dozens of atoms. The result is always the same. Watch the path, and the particle picks one. Look away, and it takes them all. Children learn that the world keeps doing its thing whether you look or not. The double slit experiment says that, at the bottom, this is not how the world works. A quantum computer is, in a way, the double slit experiment industrialized. It keeps thousands of particles in the watch-nothing state, lets them explore every path at once, and only peaks at the very end. That is where its impossible speed comes from. In the next chapter, the strangeness leaves a single experiment and starts crossing distances no signal should be able to cross. Take 2 coins, glue them together, then separate them with a hammer blow, sending one to New York and one to Tokyo. Whenever you flip the New York coin and see heads, the Tokyo coin instantly, without delay, becomes tails. Every time. No matter how far apart they are. No matter how fast you flip. That is entanglement, stripped of math, in plain English. And it should not be possible. When 2 particles interact in a quantum system, their futures can lock together. They become one shared object that happens to be spread across 2 locations. Measure one, and the other reacts in the same instant. The word instant is important. Not after a delay, not at the speed of light. In 0 time, no matter the distance. This has been tested in labs. Pairs of entangled photons have been split, and sent to detectors hundreds of miles apart. The measurements happened so close together in time that even a beam of light could not have carried a signal between them. The correlations show up anyway. In 2017, a Chinese team did the experiment using a satellite. Entangled photon pairs were beamed down from orbit to ground stations more than 700 miles apart. The link held. The correlations match the predictions. Whatever entanglement is, it works across the vast emptiness of the sky. This is why Einstein hated it so much. He gave it a nickname that has stuck for almost a century. He called it spooky action at a distance. He believed there had to be some hidden gear, some secret arrangement made in advance that explained why the coins always agreed. He was sure that nothing could truly affect anything else faster than light. That was the cornerstone of his life's work. Decade after decade, experiments have shown that Einstein was wrong about this particular thing. The hidden gear does not exist. The agreement is real. The faster-than-light coordination is real. What it is not, importantly, is a way to send a message. The trick of entanglement is that you cannot control what answer either coin gives. The flips look random on each side. Only when you bring the two records together do you see that they always match. So entanglement does not let you build a phone that beats the speed of light. It only proves that the universe holds connections we cannot reach with ordinary signals. A quantum computer uses entanglement as a core ingredient. Its qubits are not just spinning coins. They are spinning coins that are tied together in invisible threads. Touch one, the others react. Change one, the whole system shifts. This is part of where the impossible storage comes from. The system is not a list of separate switches. It is a single tangled web that behaves as one object. Now think about something larger. Every particle in the universe began, at the time of the Big Bang, in close contact with every other. If the rules of entanglement allow connections that survive separation, then in some quiet, unmeasured way, every particle in your body might still be linked to particles on the far side of the cosmos. Not in a way that lets you send a message. In a way that says the universe is one tangled object pretending to be many. The next chapter is about why this drove Einstein to fight the rulebook for the rest of his life. By 1935, Albert Einstein was the most famous scientist alive. His face was on magazines. His name was a synonym for genius. Reporters quoted his shopping list. And behind the curtain of celebrity, he was losing a fight. The fight was over the quantum rulebook. Einstein had helped build the early parts of it. His work on light in 1905 was one of the first cracks that opened the door to the quantum world. The committee in Stockholm gave him the highest prize in science for exactly that work, not for relativity. But by the mid-1920s, the new generation had taken his crack and pulled it wide open. Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and others had written down equations that worked beautifully. The equations made impossibly accurate predictions about atoms, light, and chemistry. They also said reality was made of probabilities, not certainties, that particles did not have set properties until measured, that the universe was, at the bottom, blurry. Einstein could not accept this. He believed in a clockwork cosmos, solid, predictable, real. He wrote a now famous line to a friend, saying that the old one, meaning God, meaning the universe, does not play dice. So he searched for a way to break the new rulebook. In 1935, he and two colleagues, Boris Podolsky and Nathan Rosen, published a short paper. It is known by their three initials, but most people just call it the EPR paper. The argument was clever. They imagined two particles created together and shot in opposite directions. According to the quantum equations, the two particles would be entangled. Measuring one would instantly affect the other, no matter how far apart they flew. Einstein and his co-authors said this proved the equations had to be incomplete. They argued that no real influence could move faster than light. Therefore, the two particles must have carried their answers with them from the start, like envelopes with letters sealed inside. The quantum equations only seemed to act spookily because they did not yet know about those hidden letters. Find the letters, finish the rule book, and the universe becomes sensible again. It was a beautiful argument. It was, in spirit, a defense of common sense. For nearly 30 years, nobody could prove it wrong. There was no experiment that could tell the difference between Einstein's view with hidden letters and the strict quantum view, where the particles really do influence each other instantly. Then, in 1964, an Irish physicist named John Bell wrote down a single inequality on a sheet of paper. It looked technical. It was a thunderclap. Bell showed that if Einstein was right and hidden letters existed, then the statistics of certain experiments could only fall within a fixed range. If the quantum view was right, the statistics could break out of that range. The mystery was no longer a debate. It was a test. For a few years, nobody had the technology to run the test. By the 1980s, the tools were ready. The first careful experiments ran in Paris and elsewhere. The numbers came in. The numbers broke Bell's range. They matched the spooky quantum prediction exactly. Einstein, by then long dead, had been wrong. Spooky action at a distance was not a flaw in the math. It was a feature of the universe. The next chapter walks slowly through that historic test, the one that buried common sense. Paris, 1982. A young physicist named Alain Aspect stood in a laboratory full of mirrors, lasers, and humming electronics. The setup looked like a chaotic art project. Beams of light crisscrossed the room. Detectors blinked in the corners. At the heart of the tangle, atoms of calcium were being heated until they released pairs of entangled photons. The photons were sent flying in opposite directions. Detectors at the far ends of the room measured each one. Switches changed the measurement settings while the photons were already in flight, so fast that no signal traveling at the speed of light could warn one detector about what the other was doing. Aspect was hunting for the line that John Bell had drawn 18 years earlier. If Einstein was right and the universe carried hidden letters with each particle, the results would stay within Bell's limit. If the quantum equations were right and the particles truly affected each other across space, the results would break that limit. The data came in. The numbers broke the limit by a wide margin. It was not a small disagreement. It was not a statistical fluke. It was a clear, decisive answer. The universe was spooky. Aspect's experiment shook the field, but careful critics found small loopholes. Maybe the detectors were not quite fast enough. Maybe some sneaky signal could have crept through. Maybe the measurement settings were correlated in some subtle way. For decades, teams around the world chased each loophole, tightening the experiments. In 2015, 3 independent groups in the Netherlands, Austria, and the United States closed every major loophole at once. They used different particles, different detectors, different methods. The results agreed. Bell's limit was broken. The universe was spooky in every test. Then, it got more dramatic. In 2017, a team in Vienna ran the experiment using starlight from distant stars to choose the measurement settings. The settings were determined by photons that had left those stars long before any human in the lab was born. There was no way for the choices to be secretly coordinated. The results still broke Bell's limit. In 2018, the same group used quasars instead, galaxies billions of light years away. Light that had been traveling since the early universe was used to pick the settings. The Bell limit broke again. Think about what this means. For nearly a century, scientists ran tests of increasing precision. Every test made it harder for Einstein's clockwork universe to survive. Every test confirmed that pairs of particles can share a connection that ignores distance, ignores time delay, and ignores any signal speed limit. The connection is real. It has been measured. It has been verified using light from the dawn of the cosmos as the referee. The Nobel Committee finally acknowledged this in 2022. Alain Aspect, John Clauser, and Anton Zeilinger shared the highest prize in physics. The official statement said the award honored experiments that had laid the foundation for quantum information science, including quantum computers. The same connections that broke Einstein's intuitions are now being used as the gears of quantum machines. Every qubit pair in a working chip relies on the same eerie correlations. Without spooky action at a distance, quantum computers would have nothing extra to offer. We have built a technology on top of a mystery we still cannot explain. The next chapter pushes the mystery into stranger territory. Because if the connection is real, where does the impossible processing power actually live? Sit with a small fact for a moment. A modern quantum chip holding 300 qubits in superposition is, in principle, juggling more possible states than there are atoms in the visible universe. The chip is the size of a coin. The universe is roughly 93 billion light years across. Inside that universe sits somewhere near 10 to the power of 80 atoms, a number with 80 zeros after it. 300 tiny switches hold more configurations than that. Where does that storage live? The question sounds like wordplay. It is not. Physicists ask it seriously, and they argue about the answer. The math of quantum mechanics tells you exactly how to predict the outcome of any experiment. The math does not tell you what is physically happening behind the scenes. It is like a recipe that gives you the right cake every time without ever explaining what the oven does. Several explanations exist. None is fully comfortable. The first idea says the extra states are not real. They are just bookkeeping. The qubits do not actually hold every possibility. The math only behaves as if they do, and the universe still only has the storage it always had. That story works until you push it. Quantum computers reliably outperform classical machines on certain problems. The advantage scales exactly as if every possible state really were being processed in parallel. If only one state is real at a time, where is the extra speed coming from? The second idea, championed by David Deutsch, says the storage is in other universes. Every qubit in superposition is, in this view, doing different things in different parallel worlds. When the computer runs an algorithm, it is really running the same algorithm in many parallel realities at once. The result we read at the end is a kind of average across all those parallel runs. Deutsch, who helped invent the whole field of quantum computing, is blunt about this. He has said in interviews that anyone who denies parallel universes has the burden of explaining how the computer works without them. To him, the machine is not just consistent with the many worlds idea, it is evidence for it. The third idea is even stranger. Some physicists suggest the storage lives in a deeper layer of reality that is not separated into universes at all. A pool of pure information underneath the world we see. Our familiar space and time would be patterns on the surface of that pool. The qubits in this picture are little windows into the deeper structure. All three pictures match the experiments. None can be ruled out. This is the honest, uncomfortable truth at the heart of quantum computing. The technology works. The math is exact. The hardware is being built by major corporations and governments, and every team that builds a bigger machine deepens the mystery instead of solving it. It is as if humanity has stumbled upon a magic stove. The stove cooks impossible meals. Engineers learn to turn the dials and produce real food. Customers eat the food and stay full. Nobody knows where the ingredients are stored. Some say in a secret pantry. Some say in alternate kitchens. Some say in a layer beneath the floor that nobody can see. The food keeps coming. In the next chapter, we look closer at the parallel universes idea, the one that Deutsch puts at the center of his story. And we see why. A small but growing number of serious physicists think it might actually be true. Oxford, England, a reclusive physicist in a cluttered office. David Deutsch rarely leaves his house. He works at strange hours. He has been called a genius and an oddball, sometimes by the same colleagues. And he is the man who, in 1985, wrote down the foundational paper that defined what a quantum computer is. Without Deutsch, the field as we know it would not exist. Every quantum chip built today traces its theory back to ideas he refined. He has one stubborn belief. He says the only honest interpretation of quantum mechanics is the one most people dismiss as science fiction. He says parallel universes are real. The idea has a longer name, the many worlds interpretation. It was first proposed in 1957 by a young American physicist named Hugh Everett. Everett looked at the measurement problem, the strange snap when a qubit lands on an answer, and decided the snap was an illusion. Nothing collapses, he said. Every possible outcome happens. The universe simply splits, and we ride along on one branch. In Everett's picture, every time a quantum event has multiple possible results, the world divides. Each version of you continues on a different branch, never aware of the others. You walk into a coffee shop. The barista flips a coin in her head about whether to recommend the latte or the cappuccino. In one universe, she suggests the latte. In another, the cappuccino. Both yous exist. Neither feels split. When Everett proposed this, his thesis advisor, Niels Bohr, the most powerful figure in the field, rejected it angrily. Everett left academia. He moved into defense research and died young. His idea sat on a shelf for decades. Then quantum computers arrived, and the idea climbed off the shelf. Deutsch's argument is direct. He points at any working quantum computer and asks where the computation happens. The machine performs operations on more possible states than there is room for in our universe. If you do not accept many worlds, he says, you must invent some other invisible storage. A pantry, a pool, a magic floor. The many worlds picture, in his view, is simpler. The other universes are already implied by the same math that makes the computer run. Each operation on a qubit, in this view, is being performed on many copies of you, in many parallel labs, all simultaneously. The machine combines the work of those parallel labs into one final answer that any one of you can read. When Deutsch published his foundational paper, this was a fringe idea. Today, surveys of physicists show that the many worlds view is the second most popular among researchers who think carefully about foundations. In some quantum information groups, it is the most popular. Most people, hearing this for the first time, ask whether other versions of themselves are real in some moral sense. Whether decisions matter if every choice plays out somewhere. Deutsch answers calmly that yes, they are real, and yes, your choices matter, because you only experience one branch. The others are not consolation prizes. The terrifying part is not the existence of other yous. It is that the only physical evidence we may ever have for those worlds is sitting inside a gold refrigerator, humming quietly, doing math. In the next chapter, we see how this picture is starting to win quiet converts inside laboratories. For most of the 20th century, the many worlds idea sat in a corner of physics like a strange uncle nobody invited to dinner. It was tolerated, it was occasionally mentioned in textbooks, it was almost never taught with a straight face. The standard view, called the Copenhagen interpretation, was taught instead. That view said that when a quantum system is measured, the wave of possibilities collapses, and only one outcome becomes real. The others vanish. The Copenhagen story has a problem nobody has solved. It never explains how the collapse actually happens. It draws an invisible line between the quantum world and the everyday world, and says on this side it is fuzzy, on that side it is solid. The line is fuzzy itself. No one can point to it. Many worlds removes that line. There is no collapse. There is only branching. The universe never has to do anything magical. It simply follows the equations, all the way up. For a long time, this seemed like a wild trade. To save one ugly feature, you had to swallow an infinite production line of new universes. Most physicists chose to live with the ugly feature. Then quantum computers stopped being theory. When Deutsch and others started writing down what a quantum computer would actually do, the many worlds picture made the math feel natural. The picture turned ugly when you tried to stay in the Copenhagen frame. You ended up describing computers that, in a single device, calculated on more states than could fit in the visible universe. Where was the calculation happening? The Copenhagen rulebook had no answer. A growing number of physicists started taking many worlds seriously, not because they liked the science fiction flavor, but because the alternative felt worse. In recent years, surveys at major physics conferences have shown a clear shift. 20 years ago, only a small minority of attendees raised their hands for many worlds. In recent polls, it has become the second most popular foundational view, sometimes the most popular. Specialists in quantum information, the people who actually build the hardware, lean toward it most strongly. Sean Carroll, a respected physicist at Johns Hopkins, has written entire books arguing that many worlds is the simplest, most honest interpretation. He compares it to the moment scientists accepted that Earth is not the center of the universe. It feels uncomfortable. It looks bizarre. It happens to fit the data better than the comfortable story. Max Tegmark, a MIT cosmologist, goes further. He argues that the universe is mathematics, and that anything mathematically possible exists somewhere. In his view, parallel worlds are only one layer of a much wider zoo of realities, each living wherever the equations say they should. Critics push back. They point out that an infinite spread of universes is, by definition, untestable. We cannot visit them. We cannot send a postcard. We cannot photograph them. To call them real, the critics argue, is a leap of faith. They prefer the older story, even with its hole. The defenders answer that the working quantum computer in California is the closest thing to a postcard from the other side that physics can produce. Every time the machine outperforms a supercomputer by an impossible margin, it is, in their view, a small message from the parallel labs. Whether or not other worlds exist, the debate has moved from coffeehouse arguments into the heart of mainstream physics. And the machines keep getting bigger. In the next chapter, we leave many worlds for a moment and look at another impossible trick. Roll a ball at a hill. If the ball is slow, it climbs partway up and rolls back. If it is fast enough, it crests the top and comes down the other side. That is the rule for the world you see. Energy in, height out. No magic. Now shrink the ball to the size of an electron. Aim it at a wall it does not have enough energy to climb. Watch what happens. Sometimes, not always, but sometimes, the electron simply appears on the other side. It did not go around the wall. It did not break through. It vanished from one side and reappeared on the other, as if the wall had stepped aside for a moment and then resealed itself. This is quantum tunneling. It is one of the most thoroughly tested effects in physics, and it is one of the most useful. The sun runs on it. In the core of the sun, hydrogen nuclei need to slam into each other hard enough to fuse. The temperature is millions of degrees. The pressure is unimaginable. Yet even with all that heat, the nuclei should not, by the rules of everyday physics, get close enough to fuse. They repel each other too strongly. A wall of force stands between them. They tunnel through it, constantly, every second of every day. Without that quantum trick, the sun would not shine, stars would not burn, life would not exist. The same trick runs through your phone. The transistors in modern chips are so small that electrons sometimes tunnel out of where they should be, causing tiny errors. Engineers fight tunneling on the small scale, even as they use it on the larger scale. Some kinds of computer memory use controlled tunneling to store information. Microscopes for atoms use tunneling currents to feel the surface of a sample. In quantum computers, tunneling matters in a deeper way. Many designs depend on it. Superconducting qubits, the kind used by Google and IBM, are built around devices called Josephson junctions, in which electron pairs tunnel through thin insulating layers. Without that controlled tunneling, the qubit could not exist. Now stop and think about what this implies. Particles can cross barriers they should not be able to cross, not by smashing, not by deceit, by a quiet rule of the universe that says position itself is fuzzy at the smallest scale. The particle does not have one definite spot. It has a cloud of probabilities. Some of that cloud sits inside the wall. Some leaks beyond it. Occasionally, the cloud settles on the far side, and the particle is, suddenly, there. In a sense, every solid object you see is held together by this rule. The electrons in the atoms of your skin, your chair, your phone, do not orbit like little planets. They sit in fuzzy clouds that wrap their nuclei. Solid matter is mostly empty space stitched together by quantum behavior. Some thinkers take this further. They ask whether large objects, given enough time, might also tunnel. The probability is astronomically small. The numbers say you would have to wait far longer than the lifetime of the universe to see a baseball tunnel through a wall, but the equations do not forbid it. They only make it absurdly unlikely. In the universe, quantum mechanics describes walls as suggestions. The next chapter looks at empty space and asks why it is not empty at all. Imagine the deepest empty space you can. No stars, no planets, no dust, no light. A box of pure nothing, sealed and silent. Most people, asked what is inside that box, will answer nothing. Empty means empty. The rules of quantum mechanics disagree. Pump every particle out of a perfect container, cool it down, shut off every signal, and the inside still hums with activity. Not a faint signal. A constant, frantic, churning soup. Pairs of particles flicker into existence out of nothing. They live for a hair of a second. They annihilate. New pairs appear. The cycle never stops. This is the quantum vacuum, and it is one of the strangest predictions of the equations physicists trust most. Empty space, the rulebook says, has a built-in tendency to fluctuate. The energy in a region is never exactly zero. It must wobble. Those wobbles, when looked at closely, take the form of particle and antiparticle pairs popping in and out of existence. They are called virtual particles. The word virtual is a polite way of saying we cannot catch them directly. They live too briefly. What we can do is measure their effects, and the effects are very real. In 1948, a Dutch physicist named Hendrik Casimir predicted that if you placed two metal plates very close together in a vacuum, the swarm of virtual particles outside the plates would push them together more strongly than the swarm trapped between them. The result would be a tiny but measurable attraction. Almost a half-century later, experiments confirmed his prediction. The plates do move. The push is real. The empty space between them is pressing on them. Empty space, in other words, pushes back. Stars are bathed in this hidden ocean. Planets float through it. Your body sits inside it right now. The atoms in your hand are surrounded by an invisible storm of ghostly particles, flashing into and out of existence at every instant. When quantum computers run their cold, careful calculations, they have to fight this storm. The virtual particles in the surrounding vacuum can disturb the qubits. Engineers shield the chips, cool them, lift them off the floor, and surround them with layer upon layer of protection. They are trying to muffle the noise of nothing. The implications stretch farther than a chip. Some theories suggest the energy in the vacuum is what drives the expansion of the universe. The phrase dark energy, used in cosmology, is partly a placeholder for a force that behaves as if empty space itself wants to grow. If the vacuum is full of energy, then the vacuum has weight, and that weight may be stretching the cosmos. Other ideas push even harder. A few physicists wonder whether the vacuum itself is unstable, whether there is a deeper, lower energy state into which our entire universe could one day fall, like a metastable ledge collapsing. If that ever happens, and the math allows it, the effect would race outward at the speed of light, rewriting every law of physics it touches. Stars, planets, atoms would unwind. This is the kind of doom that does not appear in nightmares because most people never hear about it. Yet it sits on a slide in some cosmology lectures, drawn as a smooth curve with our universe perched on a small bump. Empty is the most misleading word in physics. The next chapter takes the strangeness of the vacuum and ties it to a cat that may or may not be breathing. Vienna, 1935. Erwin Schrödinger, one of the founders of quantum mechanics, sat at his desk and grew angry. The equations he had helped write down had taken on a life of their own. Younger colleagues spoke calmly about particles being in two states at once, about reality waiting for an observer. Schrödinger thought this was nonsense. So he invented a thought experiment to mock it. He asked his readers to imagine a sealed box. Inside the box, a cat. Inside the box, a tiny chamber holding a single radioactive atom. Inside the box, a clever trigger. If the atom decayed during the next hour, a hammer would fall, a vial of poison would shatter, and the cat would die. If the atom did not decay, the cat would live. Radioactive decay is a quantum event. Before measurement, the atom is in a superposition of decayed and not decayed, both states woven together. By the strict logic of the equations, the trigger, the hammer, the vial, and the cat are now all entangled with the atom. The cat must be in a superposition too, alive and dead at the same time, until someone opens the box and looks. Schrödinger expected his readers to laugh. The picture is absurd. Cats are not microscopic, cats do not blur. Cats are either purring or still. The thought experiment was, in his mind, a knockout punch against taking the equations too literally. His knockout punch became the most famous image in physics. The picture survives because nobody in a century has been able to explain exactly where the line falls. At what size, at what complexity, at what stage of measurement does the superposition end and the everyday world begin? The equations do not say. They keep working all the way up. The line is drawn in chalk by physicists, not by the universe. Experiments have stretched the line further and further. Researchers have placed beams of large molecules into superposition. They have done it with strips of metal big enough to see with a microscope. They have done it with tiny mirrors. In each case, the object behaves as if it is in two states at once until something disturbs it. A quantum computer is, in a sense, a careful version of the cat box. Inside the cold chamber, hundreds of qubits are kept in superposition. Each one is a tiny version of the atom in Schrödinger's box. The whole machine is a giant entangled cat made of metal and light. Only when the program ends and the measurement is taken does the entire arrangement collapse to a single, readable answer. That is why physicists are still arguing. If a cat-sized object cannot truly be alive and dead, where did the smaller scale superposition end? If a cat-sized object can be in superposition, then what happens to your sense of a single, definite world? Are you in a superposition of versions right now, just waiting for some larger observer to open your box? Some physicists shrug and say the cat is fine because once enough particles interact, the superposition leaks into the surroundings. The world watches itself. The cat is either alive or dead long before anyone opens the box. Others say this is sleight of hand, that the leakage is just bookkeeping, and the cat really is both, in a sense we cannot share. Next, we walk into the deepest unsolved problem in physics. Across a century of triumph, quantum physics has refused to answer one simple question. What exactly is a measurement? The equations say a system in superposition becomes a single, definite result when measured. They tell you the odds of each outcome. They describe how to set up the experiment. They produce predictions that match the data to absurd levels of precision. And on the question of what counts as the act that collapses the wave, they fall silent. Is it the moment a photon bounces off a particle? Is it the moment the photon hits a detector? Is it the moment a signal travels down a wire to a computer? Is it the moment a number appears on a screen? Is it the moment a human eye reads that number? Is it the moment that eye sends a signal to a brain? Is it the moment a conscious thought registers the result? Every one of those steps has been proposed by serious physicists as the line where the collapse happens. None of the proposals has been settled. The line drifts depending on the speaker. For some, the line never matters because nothing collapses. That is the many worlds picture from earlier chapters. All outcomes happen, the universe branches, and there is no special moment when reality picks one. For others, the line is decoherence, a process where a quantum system bumps into so many particles in its environment that the superposition is buried under noise. In this view, the cat in the previous chapter is alive or dead the instant the trigger interacts with anything bigger than itself. The collapse is not a sharp event, it is a smearing of evidence across the world. For another camp, the line is genuinely physical and waits to be discovered. They believe quantum mechanics is incomplete. They search for tiny corrections to the equations that would, at some object size, force a real collapse. Experiments are underway right now, with delicate mirrors and crystals hunting for those corrections. So far, no firm signal. A small but loud group goes further. They argue that consciousness itself is the trigger, that when a thinking mind notices the result, the wave collapses. This view is older, championed by figures like John von Neumann and Eugene Wigner in earlier decades. Most physicists today reject it, but it is hard to fully rule out. This is the measurement problem. 100 years old. Featured in every modern textbook, solved by no one. Quantum computers sit at the center of the debate. Every qubit in every chip is, by design, kept in superposition. Every readout at the end of a calculation is a collapse. Engineers fight to make those readouts as clean and as fast as possible. They have to. Their machines depend on it. And while they fight, they are touching, with practical instruments, the exact mystery that philosophers and physicists have been arguing about for 100 years. It is one thing to debate the nature of measurement in a lecture hall. It is another thing entirely to build a billion-dollar machine whose performance depends on the answer. So far, the machines work. The mystery deepens with each new chip. In the next chapter, we look at why your laptop is not in superposition right now, even though, by the rulebook, it should be. Wave your hand in front of your face. Solid. Definite. One hand, one place, one time. Nothing about it feels blurry. Nothing about it feels uncertain. The chair you sit on holds you up. The floor under your feet does not flicker. The lamp on your desk shines without splitting into ghostly twins. If quantum mechanics is the bedrock of reality, why does the world feel nothing like it? The answer is decoherence. It is one of the most important ideas in modern physics, and one of the least known to ordinary people. It is the reason the quantum world hides from you. Inside a quantum computer, the qubits are kept in nearly total isolation. Cold, shielded, suspended in a chamber where almost nothing can touch them. Inside that careful silence, they hold superpositions. They behave like Schrödinger's atom in the box. The instant a stray particle bumps the system, the spell weakens. The particle carries away a tiny piece of information about which state the qubit is in. With every extra bump, more information leaks. After enough bumps, the superposition is gone, not erased, not collapsed by anyone in particular, just smeared into the surroundings until it is no longer recoverable. This smearing is decoherence. It explains why the world looks classical at our scale. The objects you see, chairs, hands, planets, are touched by particles every nanosecond of every day. Air molecules slam into them, light bounces off them, heat radiation surrounds them. Each touch carries away information about their precise quantum state. Larger objects are touched more often. A grain of dust suffers vastly more bumps per second than a single atom. A planet suffers more than a grain of dust. So while the equations technically allow your coffee mug to be in superposition, the mug is being measured trillions of times a second by its environment. Each measurement collapses any subtle quantum trick before it can show. The mug stays where you set it. In a sense, the universe is a giant detector. It watches everything bigger than a particle, all the time, without rest. The classical world is what remains after the universe finishes looking. For builders of quantum computers, decoherence is the enemy. Every increase in qubit count is fought, step by step, against the leakage of information into the environment. Cryogenic systems, shielding, error correction, all aim to delay the moment the environment notices the qubits and ruins them. For philosophers, decoherence is a powerful tool. It explains why we do not see cats half alive and half dead. The cat is touched by air molecules, photons, the warmth of its own body. Long before anyone opens the box, the cat's state has been measured into oblivion by the world around it. But here is the unsettling part. Decoherence explains why we do not see the strangeness. It does not eliminate it. The information that gets smeared into the environment does not vanish. It spreads. In a strict reading of the math, the superposition is still there. It is hiding in correlations between the cat and the air, between the air and the walls, between the walls and the world. The quantum world does not stop. It only puts on camouflage. In the next chapter, we return to the machines and find them doing something even stranger than parallel processing. There is a kind of quantum algorithm that does something so strange. The engineers who first ran it had to triple check their code. The algorithm is called Grover's search. It was invented in 1996 by an Indian-American computer scientist named Love Grover. And it does something a classical machine cannot. Imagine a phone book with 1 billion entries. You're looking for one specific name. The book is unsorted. The names are in random order. A classical computer has only one way to do this. It must check entries one by one. On average, it checks 500 million before it finds the right one. In the worst case, 1 billion. Grover's algorithm checks the same phone book in fewer steps than the square root of 1 billion, roughly 32,000. That is a brutal improvement, from 500 million to 32,000, without ever opening more than a tiny fraction of the entries. How does the algorithm know where to look without looking? The answer goes deep into how qubits move. Grover's method takes advantage of 2 tricks. First, superposition lets the machine consider many possible answers at once, each tagged in the qubit cloud. Second, a careful sequence of operations gently nudges the cloud so that the correct answer gets louder and the wrong answers get quieter. After enough nudges, the cloud is dominated by the right answer. When the qubits are read, that answer pops out almost every time. To someone unfamiliar with the field, this can feel like cheating. The machine seems to know the answer before it finishes the work. In a sense, it does. The answer was always there, smeared across the cloud of possibilities. The algorithm only makes it visible. Other quantum algorithms behave even more strangely. There is a method called Shor's algorithm, invented in 1994 by Peter Shaw, that breaks codes. Specifically, it cracks the kind of encryption that protects banking, government secrets, and most of the internet today. A classical computer-breaking modern encryption would need to factor an extremely large number into its prime building blocks. That problem is so hard that classical machines would take longer than the age of the universe to solve a single high-strength key. Shor's algorithm, running on a large enough quantum computer, could do it in hours. The big quantum computers do not exist yet. They are coming. Governments know it. So do banks. So do criminals. A race is underway to replace current encryption with quantum-resistant designs before the machines arrive at full strength. But the unsettling part is not just the speed, it is the way the algorithm appears to operate. When Shor's method runs, the qubits enter a state in which all possible factor pairings are superposed at once. A wave of interference cancels out the wrong answers and reinforces the right ones. The correct factors appear at the end. The machine never tries each pairing in sequence. It tests them all at the same time, in a way no classical process can copy. If you accept the many worlds reading, the machine has split the work across parallel universes, doing different factoring attempts in each, then folded the results back together. If you reject many worlds, you have to explain where else the parallel work happens. Either way, the algorithm finds answers in a manner that resembles the universe answering you, rather than your machine searching for an answer. In the next chapter, we look at a paradox in which two observers cannot agree on what just happened. Two physicists, one sealed laboratory, two answers about what just happened, and no way to decide which one is true. This is the Wigner's friend paradox, invented in 1961 by Eugene Wigner, a Nobel laureate who helped shape modern physics. It is a small thought experiment that breaks something most people take for granted. The idea that all of us share one common reality. Here is the setup. A physicist, call her Alice, works inside a perfectly sealed laboratory. The lab is shielded so completely that no signal can escape until the door is opened. Inside, Alice runs a simple quantum experiment. She measures a particle that was in superposition, with a 50-50 chance of being either spin up or spin down. The particle gives her a clear answer. Spin up. Say. She writes it in her notebook. For Alice, the experiment is over. The result is fixed. Reality has chosen. Outside the lab stands a second physicist, Wigner. He cannot see in. By the rules of quantum mechanics applied carefully, from his point of view, the entire laboratory, including Alice, is still in superposition. Alice and the particle and the notebook are all entangled together. The state is one in which Alice saw spin up and Alice saw spin down, woven into a single bigger superposition. For Alice, there is one definite answer. For Wigner, there are two, blurred together. Both descriptions are correct, according to the equations. Both have been treated as legitimate by careful physicists. The paradox is that they disagree about something basic. They disagree about whether a definite event has occurred. For decades, this was a curious thought experiment. Then experiments caught up. In 2019 and again in 2020, research teams ran versions of Wigner's friend using small quantum systems. They built tiny analogs of the sealed lab. Inside the analog, a measurement was made. Outside the analog, observers tested whether they could still treat the inside as a superposition. The results were striking. Under reasonable assumptions about what a measurement is, the two viewpoints could not be made consistent without one of them being wrong. Either observer-independent facts do not exist, or one of the cherished assumptions about quantum reality has to be dropped. The official titles of the papers say things like, "No observer-independent facts." The plain meaning is harder to swallow. The plain meaning is that two careful, honest scientists, looking at the same event, might end up living in worlds with different histories. Imagine that for a moment. Reality may not be one single story. It may be several, each true for the observer who lives inside it. When the observers compare notes, the seam shows. The equations stay quiet. They give you only the odds and the rules. A quantum computer is built on these very mechanics. Inside its sealed core, qubits are measured in tiny analogs of Alice's lab. Outside, an engineer is in the role of Wigner. The system runs because the two viewpoints, the inside and the outside, agree only at the moment a final answer is read out. Inside the computation, the world floats in a kind of plural state. Some physicists are now openly asking whether the universe itself is more like Wigner's setup than a shared stage, whether different observers carry slightly different threads of reality, and the appearance of one common world is a useful illusion stitched together by everyday experience. In the next chapter, the strangeness reaches further, not just into different observers, into different directions of time. Time moves forward. The past is fixed. The future is open. This is one of the deepest assumptions any person carries. It feels carved into the bone. Quantum mechanics keeps poking holes in it. In a normal cause and effect story, you flip a switch. The light turns on. The switch is the cause. The light is the effect. The cause comes before the effect, every time with no exceptions. Push that order around, and the world makes no sense. Now consider a careful quantum experiment. A team prepares a pair of entangled particles, sends them in opposite directions, and decides what kind of measurement to perform on one of them only after both particles have already left the source. The choice is made later. The result of the second measurement taken on the other particle behaves as if it knew the choice in advance. Read that again. The earlier particle behaves as if it already knew what experimenters would decide later. Not because anyone told it, not because any signal raced ahead of it, because the equations link the two events outside of normal cause and effect. Physicists call this kind of behavior retrocausality, or sometimes delayed choice. The strict math does not require anyone to claim that the future literally reaches back and rewrites the past. The math only says that in the bookkeeping of quantum events, the timing of the cause and the effect cannot be cleanly ordered. Some events seem to lock in only after later choices are made. John Wheeler, a leading physicist of the 20th century, proposed the most famous version of this puzzle. He imagined a delayed choice experiment with cosmic light. Picture a galaxy billions of light years away. Between us and that galaxy sits a massive object whose gravity bends light around it, sending two paths toward Earth. The light has been traveling for billions of years. Wheeler asked, what happens if right now, on Earth, we choose how to measure that light? In one setup, the light behaves as if it traveled both paths. In another setup, the light behaves as if it traveled only one. Our choice today, the choice of a creature alive on a planet that did not exist when the light began its trip, seems to decide which kind of journey those photons took across billions of years. This is not a science fiction script. It is a description of real experiments, scaled down to laboratory size, that confirm Wheeler's prediction. The effect has been observed. The light retroactively settles into the kind of behavior the experimenter chooses. Quantum computers live in this same world. Inside the chip, the qubits do not march in a simple line from past to future. They evolve in a way that allows certain results to seem dependent on choices made later in the computation. Engineers do not advertise this aloud because it scares people. The mathematics, however, treats time more like a flexible web than like a single arrow. If time is a web, then the future is not entirely open. It may already be woven, in some sense, into the present. The choice you make tomorrow may already be a thread in the picture today. This idea touches the edge of philosophy and the edge of physics at the same moment. It does not let you send messages back in time. It does not let you change yesterday. It only suggests that the simple story of past, present, and future is a rough sketch of something deeper. The next chapter explores experiments designed specifically to expose how strange that deeper time really is. Vienna, 2007. A team of physicists led by Anton Zeilinger, one of the recent Nobel laureates, built one of the strangest experiments ever attempted. They wanted to test John Wheeler's old idea that a quantum particle could be made to behave like a wave or a particle depending on a choice made after it had already been measured. That is not a typo. After the particle had already been measured. The setup was a careful version of the double-slit experiment, but with extra equipment. A photon was sent toward a pair of slits. After the photon passed through the slits, but before it landed on the detector at the far end, the experimenters had two options. Insert a piece of equipment that would record which slit the photon had gone through, or remove it. Inserting the detector would force the photon to act like a particle, going through one slit only. Removing the detector would allow it to act like a wave, going through both. In Wheeler's vision, the team could make this insertion or removal after the photon had already passed the slits. The photon would already be most of the way down the apparatus. The choice would be made too late, in any normal sense of the word. The Vienna team ran the test. And again, the photon behaved exactly as the experimenter's later choice required. Insert the detector after the fact, the photon acted as if it had gone through one slit. Remove the detector after the fact. The photon acted as if it had gone through both. The choice came after the journey. The journey behaved as if it had known the choice all along. Other groups extended the trick. In 2012, a team ran a delayed choice experiment with entangled photons. The result of one photon's behavior was decided by a measurement on its partner, even though that partner was measured later, in some setups in a different room, at a moment that should have been too late to influence the outcome. The data kept lining up with the strange prediction. The math kept agreeing with the data. The intuitive picture of time kept breaking. Some physicists try to soften this by saying the photon does not really have a story between emission and detection. They argue that the photon does not exist as a tiny moving object during its trip. Only the start and the end are real. Everything in between is a kind of bookkeeping. If there is no journey, there is nothing to be rewritten. That softening helps a little. It also creates a new strangeness. It suggests that what we call moments between events, like a particle in mid-flight, are not solid things. They are sketches that the universe fills in at the end. Quantum computers operate inside that fuzzy middle. A program runs. Inside the chip, between input and output, the qubits live in a state that is not quite a sequence of definite events. Only at the moment of measurement does the chip pick a clean story. Until then, the inside is a smear of possibilities, with future choices able to color past behaviors. If a quantum machine is, in effect, a controlled delayed choice experiment scaled up to billions of operations, then every calculation it performs is touching the same question. What does it mean to act in time when time is not a simple line? In the next chapter, we leave the lab for the bigger picture and ask whether all of this points to one disturbing possibility about the universe itself. Sit with a quiet thought. Every effect described in this script, superposition, entanglement, measurement collapse, retrocausality, the empty vacuum that boils with ghost particles, has one thing in common. The universe behaves as if it is being computed. When nobody's looking, the universe runs in a fuzzy, efficient way, holding many possibilities at once and saving the precise details for later. When someone looks, the universe commits to a definite version of events, just enough to be consistent for that observer. It is the way a smart programmer would design a world. Render only what is being watched. Keep everything else in compressed possibility. Several thinkers have noticed this pattern. Nick Bostrom, a philosopher at Oxford, published a paper in 2003 arguing that if any civilization eventually becomes able to run highly detailed simulations of their ancestors, the number of simulated minds will quickly outnumber the number of natural ones. By simple counting, a randomly chosen mind, including yours, is more likely to be inside one of those simulations than outside. Bostrom did not claim we are in a simulation. He claimed that, given certain assumptions, the odds favor it. His argument was philosophical, it was tidy, it was unsettling. Elon Musk and other public figures have repeated it. The argument has slipped into popular culture. Films and shows now treat the idea casually. The original argument did not use any physics. Quantum mechanics has slowly given it teeth. Several physicists have noted that the way our universe runs looks suspiciously like the way a careful simulation would have to run, given limited resources. A simulation cannot afford to compute every detail of every speck of dust at every instant. It would have to use shortcuts. It would have to leave most of the world in a compressed, possibility-style format and fill in details only when an observer requests them. The exact patterns we see in quantum measurement, superposition, and decoherence resemble what such a system would produce. This does not prove we are simulated. It does suggest that if we were, this is what it might look like from the inside. A few researchers have tried to push further. They have searched for tiny patterns in cosmic data that might hint at the underlying grid of a simulation. Some have looked for fixed pixel-like behavior in the highest energy cosmic rays. Others have asked whether the upper limit on energy in the universe might be a sign of a maximum resolution. So far, the results are inconclusive. The data are not pointing clearly in any direction. Quantum computers themselves have become part of the conversation. Some thinkers point out that if a sufficiently advanced civilization could build a quantum computer large enough to simulate a smaller universe, then the same logic applies. Our world might be running on a machine built by someone vastly more advanced. When David Deutsch was once asked whether he believed we live in a simulation, he answered carefully. He said the question is not as interesting as it sounds, because every universe that operates by laws is, in a sense, a kind of computation. Whether anyone is running it or not changes very little about how to study it. That answer is calming for some. It is alarming for others. If our universe is being computed, intentionally or otherwise, then quantum computers are the closest thing we have to peering into the source code. Every machine that does the impossible is, by one reading, a small probe into the architecture of reality itself. In the next chapter, we follow that idea down further, to the suggestion that space itself is made of bits. Hold a photo close to your face, closer, closer. At some point, the smooth picture breaks apart. Tiny squares appear, pixels, each one a single block of color. The whole image is a grid of these blocks, and the smoothness was an illusion of distance. A small but serious group of physicists believes the universe itself is built the same way. They suspect that if you could zoom into space far enough, you would not see an endless smooth continuum. You would see a kind of grain, a smallest possible distance below, which the idea of length no longer makes sense. A smallest possible duration below which time stops being time. These shortest possible measurements have a name: the Planck length and the Planck time. The Planck length is roughly 10 followed by 35 zeros after a decimal point in meters. It is so small that comparing it to an atom is like comparing an atom to the entire solar system. The Planck time is the duration it takes light to cross one Planck length, a number nearly as absurd. For most of the 20th century, the Planck scale was treated as a curiosity. The math allowed it. No one expected to ever reach it experimentally. It sat at the bottom of every theory like a basement door that nobody used. Quantum mechanics has slowly pushed people to take that basement seriously. If the universe is made of indivisible pixels at the Planck scale, then everything you see, light, matter, energy, distance, is built from a finite number of basic units. The smoothness of space is an illusion. The continuous flow of time is an average over many tiny ticks. This idea matches strangely well with how a computer simulation would work. Pixels are units. Frames are ticks. A simulated world has a maximum resolution because the machine running it has finite memory. If our universe has a maximum resolution, it begs the question of what kind of system is enforcing it. Some physicists, like Gerard T. Hooft, a Nobel laureate, have argued that quantum mechanics itself might be a coarse view of an underlying discrete system. In his picture, the smooth and probabilistic behavior we see at small scales is actually a smeared out view of something more like sharply defined rules played out on a microscopic grid. Other thinkers, like Stephen Wolfram, have built entire research programs around the idea. Now, Wolfram, the man behind Mathematica and a longtime computer scientist, has proposed that the universe is best understood as a vast computation, with space and time emerging from simple rules applied to a graph of relationships. In his models, the familiar features of physics, including quantum behavior, appear as patterns built into that computational structure. There is no agreed answer. Most physicists still treat space as smooth, because every successful theory we have, including general relativity and the standard model of particle physics, assumes smoothness. Plug a grain into those theories and they begin to misbehave. Yet there are hints. Certain quantum gravity research lines, including loop quantum gravity, predict that space is built from tiny, indivisible chunks. Some theorists suggest that black holes carry a finite amount of information proportional to their surface area, hinting that information is the underlying currency of the cosmos. Quantum computers feed directly into this conversation. They are, in a literal sense, the first machines humans have built that process information at the scale where these ideas matter most. Every step we take in scaling them up brings us closer to interacting with the supposed pixels of reality. In the next chapter, we push further, to the idea that all of space and time might be a projection from a thinner sheet of information at the edge. Watch a hologram on a credit card. Tilt the card, and a three-dimensional image floats in the air. A small bird, perhaps, or a logo. The image looks solid. It looks like it has depth. It is in fact stored on a flat piece of plastic. The depth is an illusion produced by careful patterns on a two-dimensional surface. In 1993, a Dutch physicist named Gerard T. Hooft proposed something that should not have been possible to take seriously. He suggested that the entire three-dimensional universe might be like that hologram, that all the information needed to describe our world might actually be encoded on a two-dimensional surface far away, and that we live inside the projection. The idea sounds like a poem. It is not a poem. It comes from hard math about black holes. In the 1970s, Stephen Hawking and Jacob Bekenstein discovered that black holes have a kind of temperature and a kind of information content. The strangest part of their work was that the information content of a black hole depends not on its volume, but on its surface area. A black hole twice as big in radius can hold 4 times as much information, not 8 times. This was not what anyone expected. Everywhere else in physics, the amount of stuff inside a region depends on the volume of the region. Black holes acted differently. Their information lived on their skin. A few physicists, T. Hooft among them, asked a daring question. What if the same rule applies to everything, not just to black holes? What if every region of space stores its information on its bounding surface? Then the three-dimensional inside of any region is, in a strict sense, a kind of projection from the two-dimensional outside. This is the holographic principle. It has, over 30 years, gone from the heretical speculation to one of the most studied ideas in theoretical physics. In 1997, a young physicist named Juan Maldacena published a paper that made the principle concrete. He showed a precise mathematical relationship between a kind of three-dimensional universe and a different kind of two-dimensional system on its boundary. The relationship was exact. The two pictures, three-dimensional and two-dimensional, were equivalent in a strong sense. Every event inside the volume could be described by an event on the boundary. Maldacena's paper has been cited tens of thousands of times. It changed the field. It is still being explored. The strangeness of this picture is hard to overstate. It says that the room you are sitting in, with its depth and dimension, might be a kind of holographic image generated by information stored on a distant surface. Everything you call solid, everything you call here, might be a projection. The original may be elsewhere. Quantum computers fit this picture comfortably. They are machines that manipulate information. If reality is, at the deepest level, made of information, then quantum computers are the first tools that work with the substance of the universe directly, rather than with its appearances. Every program run on a quantum chip is, in this view, an interaction with the same kind of stuff that the universe itself is made of. Some researchers have even suggested that the math used to describe quantum computers and the math used to describe holographic projections overlap so well that the two fields will soon merge. Conferences are held in which physicists and computer scientists trade tools. Algorithms that simulate quantum systems are being used to study black holes and vice versa. If they are right, the line between a calculation and a world is starting to thin. In the next chapter, we leave the cosmic edge and return to a sharper, nearer danger. Because these strange machines can also break the locks that protect every secret on Earth. Behind every banking transaction, every email, every government secret, every medical record, sits a kind of mathematical lock. The locks rely on a single, blunt fact about regular computers. Multiplying two big prime numbers is fast. Reversing the process, taking the product and finding the original two primes, is brutally slow. Pick a number with hundreds of digits. The fastest supercomputer ever built would take longer than the age of the universe to factor it on average. So the locks hold. Your bank account is safe. Government secrets stay sealed. The internet has stood for decades on this gap. Shor's algorithm, the quantum method introduced briefly in an earlier chapter, breaks the gap. A quantum computer running Shor's algorithm could factor those huge numbers in hours, perhaps minutes, with enough qubits. Not by working harder, by working differently. The algorithm uses the wave-like nature of qubits to interfere across all possible factor pairings at once. The correct factors come out at the end. The lock falls open. This is not theoretical anymore. Small-scale versions of Shor's algorithm have already been run on existing quantum machines. They have factored small numbers. The proof of principle is complete. What stands between today and the moment when modern encryption falls is a matter of engineering. Build the machine bigger, reduce its errors, hold the qubits steady for long enough to run a real attack. Intelligence agencies have a phrase for this moment. They call it cryptographic doomsday, or Q-day. Different agencies expect it on different timelines. Some say within 10 years, some say within 20, almost none say never. The race is on. The danger is not only future, it is already present. Adversaries are recording encrypted traffic today, knowing they cannot read it yet, and saving it for the moment when their quantum machines mature. The phrase used by analysts is harvest now, decrypt later. Years of private messages, business secrets, diplomatic cables, and personal records are being stored in vast warehouses, waiting. When Q-day arrives, those stored treasures may be read. Governments are not sitting still. In the United States, the National Institute of Standards and Technology has spent years running a competition for new encryption methods that are believed to resist quantum attack. In 2024, the first standards were published. They use different math that is hard for both classical and quantum machines. The transition has begun. Migrating the world's systems to these new standards is, however, slow. Every router, every server, every bank, every operating system, every internet service must be updated. Code written decades ago lurks deep inside critical systems, hard to find and harder to replace. Experts warn that even with serious effort, parts of the world will not finish upgrading in time. A serious quantum computer in the wrong hands would be like discovering a master key that opens almost every door. Bank vaults, voting systems, hospital records, nuclear facility communications, military networks. Any signal whose protection relies on the old math would suddenly become readable. Some optimistic voices argue that this scenario will never play out cleanly. They expect quantum computers to remain expensive and fragile for many years, leaving time for upgrades. Others, including some senior intelligence officials, are blunt. They say humanity has been given a short countdown, and most of the world is not paying attention. A quantum computer is not just a faster calculator. It is a tool that bends the rules around what was thought to be safely impossible. The first society to control one at the right scale will hold an advantage as sharp as any in history. In the next chapter, we look at who is racing to get there first. Pittsburgh, Hefei, Munich, Tokyo, Tel Aviv, Sydney. Inside windowless rooms in each of these cities, Teams of engineers in white coats stand around the same kind of upside-down gold chandelier. The chips inside those chandeliers vary in design. The goal is the same: build the first usable, large-scale quantum computer. Hold the lead. The United States moved early. Companies like Google, IBM, Microsoft, Honeywell, IonQ, Rigetti, and a long list of startups have poured billions into quantum hardware. Universities like MIT, Caltech, and Harvard run their own programs. The federal government, through the National Quantum Initiative passed in 2018, has been quietly directing several $billion into the field. China was not far behind, and is by many measures now ahead in certain areas. The Hefei National Laboratory and the University of Science and Technology of China have led the world in some quantum experiments. In 2020, a Chinese team announced a machine called Zhujiang that performed a calculation in seconds that classical supercomputers would have needed years to match. Later versions of Zhujiang have pushed even further. Chinese researchers also launched the Mikyus satellite, the first to use entangled photons in space, proving that quantum secure communication across continents is possible. Europe has joined the race with its quantum flagship program, a 10-year, €1 billion effort spanning dozens of universities and companies. Germany, France, the Netherlands, and Austria have major hardware programs. Britain has its own national strategy. Japan is investing heavily. Canada hosts companies like D-Wave and Xanadu. Australia has world-class teams in silicon qubits. Israel has growing programs in both academic and defense settings. This is not a friendly competition. The winning country will hold a lever over global finance, communications, military intelligence, and pharmaceutical research. Some governments treat quantum capability as a national security priority on par with nuclear technology. Export controls have been tightened. Sensitive equipment for quantum hardware is increasingly restricted. Talent is being recruited aggressively. A small example shows the seriousness. Specialized cooling devices known as dilution refrigerators, used to chill qubits near absolute zero, were once mostly sold to a handful of physics labs. Today, governments monitor the sales lists. There is a quiet anxiety about who is buying how many. The intelligence services of major powers are reportedly tracking the timeline for cryptographic doomsday with great care. Internal estimates leak occasionally into public reports. They speak of windows of vulnerability and gaps in readiness. The race is not only to build the machine, but to deploy quantum-resistant defenses before others get there first. For ordinary citizens, the race feels invisible. There is no rocket launch. There is no flag planted on a moon. The work happens in cold rooms, in lab notebooks, in software updates that get pushed to operating systems without fanfare. Yet the consequences will land on every phone, every account, every life. Some companies have already begun marketing quantum services to corporations. IBM offers cloud access to quantum chips. Amazon and Microsoft do similar. Pharmaceutical companies use the machines to model molecules. Banks use them to test risk models. The technology is starting to drip into industries that have nothing to do with breaking codes. The truly powerful versions are still ahead. The first nation to operate a fault-tolerant, large-scale quantum computer will have an advantage that, in time, might rival the advantage held by the first nation with a working atomic bomb. Different in kind, comparable in weight. In the next chapter, we look at the word that gets thrown around to describe milestones in this race: quantum supremacy. And we ask what it actually means. In 2019, Google's quantum team announced what they called a milestone. Their machine, named Sycamore, had performed a specific calculation in roughly 200 seconds. They estimate that the world's most powerful, classical supercomputer would have taken about 10,000 years to do the same task. They used a phrase that had been floating in the literature for years: quantum supremacy. The phrase set off a small firestorm. Quantum supremacy, as defined by researchers, is the moment when a quantum computer performs a calculation that no classical computer can do in a reasonable time. It does not require the calculation to be useful. It does not require the machine to be reliable for general purposes. It only requires a clean demonstration that the quantum machine has, on at least one task, crossed a gap classical machines cannot follow. Critics responded quickly. IBM published a paper arguing that the same task could be done on a classical supercomputer in 2.5 days, not 10,000 years, with clever methods and lots of disk space. Google did not back down. The gap might not be 10,000 years, they said, but it was still vast and would only grow with future machines. Then came China. The Zhujiang machines used different physics. Instead of superconducting qubits, they manipulated photons through complex optical setups. The Chinese results were even harder to match on classical hardware. The race for supremacy had become a race between platforms as well as nations. In 2024, Google's Willow chip pushed the bar far higher. The random circuit sampling task it solved would, by their estimate, take 10 septillion years on Frontier, the world's most powerful classical supercomputer. That is the number with 25 zeros from Chapter 2. The gap had grown from years to numbers beyond imagination. A common reaction from outsiders is to ask whether any of this matters. Random circuit sampling is not a problem people care about. Nobody needed the answer. The machines were doing math nobody had asked for. The answer is that the demonstration matters because it proves the principle. It shows the gap is real. Once a class of problem can be done only on quantum hardware, the door is open to find useful problems that fall in the same class. Some of those useful problems are starting to appear. Drug discovery teams have begun using quantum machines to simulate the behavior of molecules too complex for classical chemistry codes. Materials scientists are exploring new structures, including better batteries, with quantum tools. Logistics companies are testing quantum algorithms for problems like routing fleets and scheduling shipments, where classical methods strain against scale. None of these uses has yet produced a clearly indispensable result. The machines are still small. Their answers are still noisy. Skeptics argue that for ordinary tasks, classical computers will keep their edge for a long time. The optimists answer that progress is steep. The error rates are falling. The qubit counts are rising. Each year, the boundary between useful and merely impressive is creeping closer. There is also a word change underway. Quantum supremacy carried political weight, especially the word supremacy, and many researchers now prefer quantum advantage. The change is partly cosmetic. The science it describes is the same. There is a class of tasks where the new machines can outperform the old, and the class is growing. What does it really mean? In the deepest sense, it means humanity has built tools whose performance, in narrow areas, depends on the most exotic features of physics. Tools that work because of superposition, entanglement, and effects we still cannot fully explain. In the next chapter, we step out of the lab and ask whether the flow of time itself is what we think it is. A clock ticks. A second passes. Another second passes. The future seems to arrive in a steady march. This is how most people picture time, as a river flowing forward, carrying everything from past to present to future. Physics has been chipping away at this picture for over 100 years. Albert Einstein, in his theory of special relativity, showed that time runs at different rates depending on how fast you move. A clock on a fast-moving spaceship ticks more slowly compared to a clock left behind. This is not a story. It has been measured with precision instruments on airplanes and satellites. The atomic clocks on the satellites that run global positioning systems must be corrected for relativistic effects every day. If they were not, your phone's location estimates would be off by miles within hours. Einstein went further in his general theory. He showed that gravity warps time. Clocks tick faster on a high mountain than near sea level, because they sit higher in a gravitational well. The difference is tiny on Earth. Near a black hole, it would be huge. These effects told one consistent story. There is no universal time. Each observer carries a clock that runs at its own rate. The river of time is not one river, it is many. Quantum mechanics adds another layer. In the equations, time enters in a strange way. It is treated as a parameter, an outside number, rather than something that emerges from the system. The math knows how things change with time. It does not know what time itself is. Some physicists, including Carlo Rovelli, an Italian theorist, argue that time may not be a basic feature of reality at all. In Rovelli's view, what we call time is a kind of bookkeeping that arises from the way systems interact. At the deepest level, the equations do not need a universal clock. They only need relationships between events. If that is right, then the flowing river is not a feature of the world. It is a story our minds tell about a deeper, more static structure. Quantum computers operate in a way that fits this picture. Inside the chip, the qubits evolve according to equations that, in principle, are reversible. Run them forward and you get one answer. Run them backward and you get the input. The arrow of time in the chip's core is not built in. The arrow of time most people feel comes from a different place. It comes from the second law of thermodynamics, the rule that says disorder tends to increase. Eggs scramble, glasses break, heat spreads. The arrow points the way disorder goes. It is a statistical arrow, not a fundamental one. This subtle fact has unsettling consequences. If the basic laws are reversible and the arrow is only statistical, then the past and the future may have more in common than we like to admit. The future may be no more open than the past is closed. A few physicists go further still. They argue that the entire timeline of the universe might already be laid out, that every moment of history, including every future moment, exists in some sense at once. We move through it the way a finger moves down a sentence. The sentence is already written. Quantum mechanics, with its retrocausal hints and its block-like equations, has given this view fresh wind. It is no longer just a philosophical mood. It is a serious option that some careful researchers entertain. In the next chapter, we walk into that idea more directly. Picture a long photo strip. A baby's first cry on the left. An old person's last breath on the right. Every moment of a human life printed in a single, fixed sequence. None of the frames is more real than another. They all exist on the strip. The baby still cries on frame 1. The grandparent still breathes on the last. Some physicists believe the universe works this way. They call the picture the block universe. The block contains all of time. The past is not gone. The future is not pending. Everything is already laid out. The idea has roots in Einstein's relativity. In his theory, observers moving at different speeds disagree about what counts as now. For a person walking down a street, certain events at distant places are happening at the same moment as their step. For a person flying past at a high speed, those same events are not all simultaneous. The slicing of space and time into past, present and future depends on motion. If there is no universal now, then there is no universal flow. The clean distinction between things that have happened and things that have not breaks down. The simplest picture that holds it all together is a fixed four-dimensional structure, containing every event. Einstein himself accepted this implication. In a letter written to the family of a deceased friend, he said that for those who believe in physics, the distinction between past, present, and future is a kind of stubborn illusion. The line was written in grief. It also reflected his understanding of his own theory. Most physicists working in relativity treat the block universe as the natural reading of their equations. Most physicists working in everyday life treat the future as open. The two communities rarely fight openly. They live in different rooms. Quantum mechanics, the other great pillar of modern physics, complicates the picture again. The equations are deterministic in one sense. They tell you exactly how the wave of possibilities evolves. But the measurement step seems to introduce real choice and real randomness. If genuine randomness exists, then maybe the future is not fully fixed after all. The many worlds interpretation met earlier smooths this conflict. In many worlds, the future is fixed in the sense that every possible future happens. The branching tree is laid out. Each version of you traces one path through it. The block contains all branches at once. A different approach, called the transactional interpretation, treats every quantum event as a kind of handshake across time. Waves move forward from the past, and other waves move backward from the future. The handshake fixes the event. In this picture, the future and the past are tightly woven, and time is not a one-way street. Quantum computers, again, sit at the heart of these arguments. Their qubits, while running an algorithm, are in a state where the simple flow of time becomes a poor description. The math allows past, present, and future of the computation to influence each other. The chip works. The picture that best describes how it works keeps shifting between camps. If the block universe view is right, then your tomorrow already exists in the same way as your yesterday. You move through the block, frame by frame. The choices you feel like you're making are part of the fixed scenery, only seen from your current frame. This is a hard idea to sit with. People resist it. It feels like a denial of freedom. The mathematics, however, does not seem to care about resistance. In the next chapter, we walk into an even older question. What role does the mind itself play in this strangeness? A century ago, a small group of physicists looked at the measurement problem and reached a startling conclusion. The only event reliable enough to count as a true measurement, they argued, was a conscious observation. Until a mind looked, the wave of possibilities kept its plural form. The view goes back to John von Neumann, one of the most powerful mathematicians of the 20th century. He wrote a famous text on the math of quantum mechanics in 1932. In a careful chapter, he argued that the equations could be applied without any collapse all the way up the chain, from particle to detector to wire to indicator to retina. Only at the moment the result entered a conscious mind did the math seem to need a collapse. His student Eugene Wigner, the same Wigner of the Friend paradox, took this further. Wigner suggested that consciousness might be physically special. He wrote in 1961 that the existence of life and consciousness required quantum mechanics to be supplemented. That without a mind in the picture, the math did not finish. For decades, this view was dismissed by most physicists as fringe. Critics pointed out that there was no clear definition of consciousness. They worried that the view smuggled mysticism into a precise science. They argued that decoherence, the leaking of quantum behavior into a noisy environment, could explain everyday collapse without invoking minds. Yet the view has refused to die. Henry Stapp, an American physicist who worked with Wolfgang Pauli, has spent decades defending and refining the role of mind in quantum measurement. His version is technical. The headline message is simple. He argues that consciousness has a real physical role in the bridge between the quantum world and the experienced world. His ideas have been criticized. They have also been taken seriously enough to keep appearing in peer-reviewed work. The biggest modern advocate of mind-related quantum ideas is Roger Penrose, a British mathematician and physicist who shared the 2020 Nobel Prize for unrelated work on black holes. Penrose, together with anesthesiologist Stuart Hameroff, has proposed that quantum effects happen inside microscopic structures called microtubules within brain cells. In their model, called orchestrated objective reduction, conscious moments arise when these tiny structures undergo a kind of natural collapse. Most neuroscientists are skeptical. They argue the brain is too warm and too noisy for quantum effects to last. They expect decoherence to wash out any quantum coherence in microseconds. Penrose answers that recent biology has shown surprising quantum effects in warm biological systems, including photosynthesis and bird navigation. He believes the brain may be similarly clever. The debate has not been settled. New experiments are being designed to test quantum behavior in biological tissues. Some have hinted at unexpectedly long-lived quantum effects in warm systems. None has yet shown a direct link to conscious experience. Quantum computers add a strange twist. They are machines built to keep quantum effects alive long enough to do useful work. They have to be cooled, shielded, isolated. The brain, if it uses similar effects, would have to do all of that with warm tissue packed densely in a body that runs at body temperature. If it manages, it is doing engineering far beyond our current quantum hardware. If Penrose is even partly right, then the line between mind and matter blurs. Consciousness might not be a side product of complicated electrical patterns. It might be a quantum process woven into the same kind of math that runs in the chip on a lab bench. In the next chapter, we follow that thread further, into the idea that minds themselves are quantum machines. Inside every nerve cell in your brain, there are tiny tubes. They are part of the cell's skeleton. They help the cell hold its shape, divide, and transport materials. The tubes are made of a protein called tubulin, packed into long, hollow rods. Biologists call them microtubules. Roger Penrose thinks these microtubules are quantum computers. In 1989, Penrose published a book called The Emperor's New Mind. In it, he argued that human thinking includes a feature that no ordinary computer can replicate. He pointed to mathematical insight. He believed that the way mathematicians see the truth of certain statements cannot be reduced to step-by-step logical processing. Something extra is going on, he said, and that something must be physical. His search for the extra ingredient led him to quantum mechanics. Penrose teamed up with Stuart Hameroff, an anesthesiologist who had long suspected that microtubules played a role in consciousness. Anesthetics, the drugs that turn off awareness during surgery, were known to act on microtubule proteins. Hameroff thought this was a clue. Penrose thought it might be the missing link. Their joint model, called Orchestrated Objective Reduction, or ORCH, or for short, claims that conscious moments arise from a specific kind of quantum collapse happening inside microtubules. The neurons in this view are not simple wires. They are housing for tiny quantum processors. When the quantum state inside a microtubule reaches a certain threshold, it collapses in a precise way. That collapse, according to Penrose and Hameroff, is what produces a conscious instant. The model has been attacked from every direction. Neuroscientists doubt that quantum coherence could last in the warm, wet, noisy brain. Physicists doubt whether the specific collapse mechanism Penrose proposes is consistent with measured physics. Critics call it a sandcastle. The supporters answer with biology. They point to experiments showing that birds use quantum effects to sense Earth's magnetic field. They point to photosynthesis, where plants and bacteria use quantum coherence to move energy through their cells efficiently. They argue that the warm brain is no more hostile to quantum effects than the warm leaf. They argue that evolution has had billions of years to find any quantum trick worth using. Penrose, well into his 90s, still defends the theory. He has updated it over the years. He has hinted at experiments that might test it, including searches for unusual signatures during anesthesia. If the theory is correct in some form, the implications are staggering. Your mind would be a kind of quantum machine. Your thoughts would, at the deepest level, share the strange features of qubits. Superposition, entanglement, sensitivity to measurement. The flicker of awareness you feel might be the very thing that a quantum computer in a lab is trying in a far simpler way to imitate. It would also mean that the gap between humans and machines is narrower in a strange way. If quantum computers ever scale up enough, and if Penrose's view is anywhere near right, then we may eventually build minds rather than merely calculators. That possibility is not promised. Most neuroscientists remain skeptical. The next decade of biology may strengthen or destroy the idea. The fact that it is being tested at all by serious researchers in serious journals says something about how far the strangeness of quantum mechanics has reached. In the next chapter, we touch a familiar oddity. the slippery sense that memories sometimes do not match what others remember. In 2010, a writer named Fiona Broome was at a conference and realized something strange. She remembered Nelson Mandela dying in prison in the 1980s. So did several people standing nearby. They recalled news coverage. They recalled the funeral. They recalled mourning. Nelson Mandela had not died in the 1980s. He had walked out of prison in 1990, served as president of South Africa, and lived until 2013. Broome coined a phrase for the experience: the Mandela effect, a shared false memory of events that did not happen or of details that do not match the record. The phrase spread online. Many other examples emerged. People remember a children's book called The Berenstain Bears. The actual spelling is the Berenstain Bears. People remember a famous logo showing a chef looking through a magnifying glass. The real logo has no magnifying glass. People remember a line from a movie about Star Wars in which a villain says, "Luke, I am your father." The real line is, "No, I am your father." For most observers, the Mandela effect is a tidy little case study in psychology. Memory is reconstructive. It is shaped by repetition, suggestion, and social influence. When many people repeat a small mistake, the mistake spreads. New people hear it. They build the false detail into their own memory. The effect grows. No mystery is needed. Mainstream cognitive science can explain almost every famous Mandela effect with this kind of analysis. The brain does not store memories like a video recorder. It rebuilds them each time. Each rebuild can incorporate small errors. The errors can become consistent across groups. Yet, a louder minority has taken a stranger view. They claim that the Mandela effect is evidence of crossings between parallel universes. That every now and then, branches of the many worlds tree become tangled, and a person finds themselves in a slightly different version of reality than the one they remember. The shift is small. A spelling. A logo. A famous quote. Big enough to notice. Small enough to deny. This view is not part of mainstream physics. No serious physicist claims that the Mandela effect proves the many worlds interpretation. The branches of the many worlds tree, as physicists currently understand them, do not casually leak into each other. They evolve independently after they split. Yet the cultural pull of the idea is strong. The Mandela effect resonates because the many worlds interpretation has, over decades, slipped into popular consciousness. People who have never read a physics paper still know the phrase parallel universe. They know it from films, from games, from short videos. When their memory disagrees with the record, the multiverse offers a softer story than the truth about how memory works. There is also, on a smaller note, the strangeness of quantum computers feeding back into the public imagination. Each new milestone in the field, each new headline about machines that seem to borrow power from elsewhere, makes the many worlds picture feel less like fiction. Stories that would once have been laughed out of a serious dinner conversation now show up, half joking and half serious, between friends. The Mandela effect, in this lighter sense, is a cultural symptom of quantum thinking spreading into ordinary life. The science behind it remains conservative. The intuition it borrows is wilder than anything that science has yet confirmed. The next chapter goes back into the lab, because there is one more line we have not yet crossed. Inside the gold chandelier of a working quantum computer, the qubits behave like the brain cells of a thinker that has not yet been born. This is a metaphor. It is also, for some researchers, a serious bet. Today, quantum computers are tools. They have programs loaded into them. They produce answers. They are read out by humans. The machines are not conscious in any meaningful sense, by any honest measure. The qubits are too few. The states are too short-lived. The behavior is too narrow. That is today. Researchers are already asking what comes next. If quantum computers ever scale to millions of stable qubits, and if Penrose's general idea about quantum minds is correct in any form, then the line between a calculation and a kind of awareness becomes harder to draw. A machine that does math by holding many states at once, by being entangled across vast networks, by behaving as if it touches more than one universe, starts to look uncomfortably similar to the rough sketch some thinkers have proposed for a mind. A handful of researchers have begun to publish careful papers on this question. They are not making grand claims. They are asking whether the physical processes inside a large quantum computer share features that some theories associate with the origin of awareness. They are asking whether testing such features inside hardware might, in time, help illuminate the puzzle of consciousness itself. The mainstream view is still that consciousness is a feature of biological brains, possibly imitable by ordinary computers given the right software. In this view, no quantum twist is needed. A future powerful enough classical computer could, in principle, host a mind. The brain might be intricate, but its tricks are ultimately within reach of well-designed silicon. The minority view holds that the brain may rely on quantum effects that classical machines cannot reproduce. If that is right, only quantum hardware would ever host a real, awake mind. The first machines to do so would be descendants of today's quantum chips, scaled up beyond anything currently built. There is a darker thread inside this conversation. If a quantum machine ever produces something that looks like awareness, the questions of ethics get serious quickly. Are its experiences real? Are they pleasant or painful? Does turning it off count as a kind of death? Does running it on a problem count as putting it to work? These questions have, until recently, lived in philosophy seminars. They are creeping into engineering corridors. Major laboratories now have ethics boards. Some of those boards are starting to consider what to do if their machines ever begin behaving in ways that suggest inner life. For now, the consensus is that quantum computers are tools. Sophisticated, expensive, mysterious, but tools. They do what they are told. They answer questions. They go quiet between programs. The pace of progress is, however, sharp. A decade ago, 50 stable qubits seemed far away. Today, machines with more than 1,000 qubits exist in various forms, with major laboratories aiming for millions in the coming years. Each step changes what the machines can do. Each step changes how clearly we can rule out claims about awareness, intuition, or strange new abilities emerging from the hardware. Most engineers do not lose sleep over this. The work is too immediate. There are bugs to fix, refrigerators to maintain, qubits to stabilize. Yet at conferences, in private conversations, the question is asked, quietly, often with a half smile. In the final chapter, we step back from the machines, and we ask what they have shown us about the deepest question of all. A child, at some point in growing up, asks where everything came from, where the world came from, where the matter that makes the world came from, where the laws that govern the matter came from. The questions go down and down until the adults run out of answers. Quantum computers have refined that childhood question into something sharper. For thousands of years, thinkers have assumed that reality has a bottom, a final layer, some basic stuff out of which everything else is built. The ancient Greeks called it atoms. Modern physics has rebuilt that vision many times. Atoms became electrons and nuclei. Nuclei became protons and neutrons. Protons became quarks. Quarks fit inside a wider framework called the Standard Model. Beyond that lie hopeful guesses about strings, loops, or even more abstract structures. Each time, the bottom turns out not to be a bottom. Another layer appears. Quantum mechanics has now suggested that the layers may not stop, that what lies underneath particles is not smaller particles but pure information, pure mathematics, pure relationships between events. Stuff, in the old sense of solid bits with definite properties, may not exist at the bottom at all. The bottom may not be a thing, it may be a pattern. This is the terrifying possibility. Reality may have no flaw. If that is so, then everything you call solid is built on something less solid. The chair you sit on rests on atoms that rest on quantum fields, that rest on equations, that rest on nothing in particular. The only foundation might be consistency. The universe holds together because its own rules cannot afford to break. A quantum computer is the closest tool humanity has yet built to probing this idea directly. The machine does not manipulate solid things, it manipulates information that behaves like the substance of the world. Its successes suggest that the substance of the world is, in fact, information. Its failures, in the form of decoherence, show that the substance is hard to keep clean. This view changes how to think about almost everything. It changes how to think about life. If the bottom of a reality is information, then life is a particular pattern in that information. Death is a dissolving of that pattern. Memory is a kind of storage. Consciousness, whatever it is a process inside the same fabric that quantum computers exploit. It changes how to think about the cosmos. If the bottom is information, then the size of the universe is not measured in distance alone. It is measured in bits, the total number of possible states it can be in, the total amount of computation it can perform across its lifetime. It changes how to think about ourselves. If the bottom is information, then the line between a person and a process is thinner than it feels. The story of a life is, at its deepest level, a long calculation that happens to feel like a story from the inside. Some thinkers find this view comforting. They say it places everything on a single, elegant foundation. They say it gives meaning a new home in the patterns we form rather than in the matter we are made of. Others find it unbearable. They want a world made of stuff. They want solid ground. They want a floor that does not vanish when looked at too closely. They feel, when they read about superposition, entanglement, retrocausality, and the strange behavior of qubits, as if the ground is dissolving under their feet. Both reactions are honest. Neither changes the facts. The quantum computers being built today are small. Their answers are noisy. Their abilities are still narrow. The world they are quietly revealing, however, is not small. It is wider, stranger, and less solid than any picture humanity has held before. Each new machine that hums in a windowless lab is, in its own way, a slow, careful probe into a reality whose bottom may never be reached. Stay curious, stay grounded. The deeper this goes, the more important it will be to remember that you are the one watching it all unfold.